So common ion effect in buffers. We use them all. We use this common ion effect all the time. I mean, with soil science, if you want to, how fertilizers work and getting the most out of the soil, it's a common ion effect. Mining, we use our aquifer common ion effect. We use the common ion effect to make the water less hard so our soaps can work better, get the calcium out of there and things. Okay? And then I think kind of a special case is buffers. I mean, it shouldn't be a separate category because it really is the common ion effect, how buffers work. But buffers are really, really powerful, central to a lot of different things. For example, your blood is buffered. If it wasn't, you could turn into Homer Simpson. It's due to the common ion effect that soda can leach all the calcium out of your bones and get osteoporosis. The argument is it better to drink beer instead? Well, choose your evil, right? Because you can become an alcoholic with alcohol. Well, beer's got a lot of good carbohydrates in there. So, in a few words, Ray, what would you say the common ion effect is? One way to look at it is whose principle starts with an L? Le Chatelier. I don't know if I could spell it, but Le Chatelier's principle, right? You add some product. Oh, now we got too much product, so it shifts to reactants, right? So that sort of thing, I think, is the common ion effect. If we take a look, Mariella, at the ionization reaction for HCN, right, the Ka reaction, how would you write it? HCN goes to H plus and HCN minus. Okay. So let's say you wait around long enough, you take the calculate the concentration of the products over the reactants, and you get the Ka. You look it up, it's the same. So it's at equilibrium. What's going to happen to the moles of H plus if we do the following? You add some HCN. Mallory, what's going to happen to the moles of H plus? It's going to give us more H plus because now you've got too much reactant. It's got to shift and get rid of that excess reactant. Right. We add some sodium cyanide, solid, Victoria. Yeah. Yeah. So the amount of H plus is going to go down, right? Because you hear all that? She recognized the sodium's not going to do anything. Why is the sodium there in the first place? Just so that to neutralize the cyanide. Otherwise, you can't grab a bottle of the stuff. There's no other way to physically add cyanide. You have to add a cation with it. You can't just add, right? You can't touch the bottle or the solution of it. Everything has to be neutral. And that's really like that sodium. That's really the solubility rule. Remember all those ions, group 1, sodium, lithium, potassium. They're always spectator ions. When you see this kind of thing, you don't even look at it. You see, oh, I'm just adding cyanide. There's no acidic or basic properties or anything. The only purpose is to get it in solution. All right. So I forgot to write left. Thank you. Okay. Buffers. Still a common ion effect, but it's all over the place and highly applicable. Commercial products, what's going on inside your body, everything. A buffer is a solution that has the ability to resist, although slight changes in pH. Okay, when we're going to add some acid or base, the pH really doesn't change. Even though you add some strong acid, the pH really doesn't change. Vanessa, all blank are mixtures of a conjugate acid and its conjugate base. All buffers are. And the reason being is, well, if you add an acid, Oh, you add HCl. The conjugate, what will react? The conjugate acid. So the conjugate base, because something has to react with that HCl you just added. If something doesn't react, the pH is going to drop like a rock. So something better react with it. So you add some strong acid, the conjugate base will react. Add some strong base, the conjugate acid will react. Okay, so that's how it's going to maintain this pH. Lewis, any solution can be used as a buffer. Now, if you say strong, where you get screwed is you add some acid. Or you have a solution of a strong acid. You add some acid to it. There's nothing to react with that excess acid you just added. Because the conjugate base of a strong acid, and you shouldn't even call it a conjugate base, because it can't react with anything. It's too weak. So strong acid is not a buffer system. A weak acid. If you have a weak acid, that means you've got appreciable amounts of conjugate acid, you've got some conjugate base in there, and it can handle whatever you throw at it. So weak acids, they're all buffer systems. Okay, now just how do they do it? Buffer solutions keep their acidity acting with the acid or base that you're going to add to it. Okay, so here's an example of a buffer system. HF, the weak acid hydrofluoric acid. It's a weak acid, so it's a buffer system. Adrian, in this system, the conjugate acid is HF, and then everybody, the conjugate base, F. Okay, any acid is added. Acid, and all your homework, but if you add any acid to this buffer, Sylvia, what will react with it? Well, the very first, I'm going to catch it. If we add some acid to this buffer, what would react with it? The F. It has to be the conjugate base, right? The conjugate base has to react. Okay, now if the conjugate base reacts with that acid, it's going to end up producing what, Jessica Rojas? HF. She sees it. She saw it. F minus reacts. What does it get converted into? HF. Okay. However, if we add a base, what's going to react? Bobby, what's going to react if we add a base? Add some sodium hydroxide. The conjugate acid. Exactly. The conjugate acid has to react. And it's going to produce F negative. Okay. It has to, because if it's going to react, it's got to get converted into something. It gets converted into its conjugate base. So the pH isn't going to stay level. It's going to change a little bit, but not near as much as it should have if you had a strong acid or a strong base. We add 250 mils of 0.1 molar HCl. Mateo. The number of moles of F minus should what? We're adding a strong acid.
F minus would
because what's gonna react with that strong acid he's talking about? The conjugate base, which is F minus. So if it's reacting, its amount has to go down, right? Because it's reacting. Does that make sense? Okay. Now hang on. One step at a time. This is logic-wise. So we have F minus is going to react with the acid that we added. So its amount is going to decrease. By what amount exactly? Amanda, any ideas how to figure that out? Okay, think of it this way. If we add 1 HCl unit, F minus units will react. 1, right? Because it's 1 to 1. If I had 1 mole of HCl, how many moles of F minus would react? 1. So when you see this, just I can remember When they give you volume and concentration, didn't they just tell you moles? They did. Now, there's a couple ways to get it. I don't know if you remember. How we did it, I think, didn't we set up this big equation? Big M was what over what? Moles over liters. Okay, so then there's 3 variables. They always give us 2. We solve for the third. Now, big M in this case is 0.1. Well, 0.1 has to equal what over what? Moles over liters. There you go, the 0.25 liters. Okay, so then we can find our moles. So 0.25 times 0.1 should just be 0.025. So that's how many moles of HCl we have. We added 0.025 moles of HCl. So what's the amount that the F minus should decrease by? 0.025, the exact same amount. Well, if F minus reacts, the number of moles of HF must increase. By exactly how much? The same amount. Exactly. Okay. Okay. Because the F minus has to get converted into something. Okay. Now, with all this going on in the background, the pH, you add HCl, the pH should go what? Down. And it should drop a lot because we're adding a strong acid. Now, if you have a buffer, it's still going to drop. Hardly measure it. It's going to be a very small amount. Okay? Let's see what it... Now, how do you predict these things? The Henderson-Hasselbalch equation. Now, here's one of them. pH equals pKa plus the log of the conjugate base or the conjugate acid. Concentration. And, you know, because all buffers have to have them in there. And we could do ice. We could do ice, but this is going to be a lot easier because they're always after, what's the pH of the buffer? What's the pH of the buffer? The Henderson-Hasselbalch, all he really did is just rearrange ice, and it's just a lot easier. But I like this way better. The equation I give you the Henderson-Hasselbalch one. The bottom one is easier to use. What changed? Yeah, I changed all the concentrations to moles. What stays constant? I guess how did I go from one to the other? Because this bottom one that I say is easier is going to be easier because all we do is plug in the moles of each one. We don't care about volume. Not the moles are the same. The volume. It's just your blood, right? It's a set volume. It's not going to change on you. The volume for the conjugate base is the same as the volume of the conjugate acid. I mean, it's all the same solution, the same beaker, the same blood system or whatever. So the volume doesn't matter. So it's just one less thing to worry about. So I like doing it this way. Now, if we're going to use this Henderson-Hasselbalch equation, especially the revised one, the one I like, pKa, we have to know what it is and how to get it. Jessica Vaughn, she just left. Alexa, what's pKa? pKa. I'll give you a hint. What was the equation for pH? Negative log of concentration of H. What was negative log of OH? So then pKa must be negative log of Ka. So that's the little p function. The little p function just means negative log. Negative log of Ka. Where do you get the Kas? Yeah, all that list of tables of Kas. Right. Okay. This is what the problems look like. A buffer. This is how they made it. They put 50 mils of 0.25 molar sodium cyanide to 40 mils of 0.2 molar HCN. And I give you the Ka. Javier, every buffer has to have a conjugate acid and a conjugate base. What's the conjugate acid and the conjugate base in this system? The acid would be HCN. What would be the conjugate base? Now, what I'm after is try to leave the Na part out, because it just looks more complicated. Think of it as cyanide, right? Cn minus. Cyanide should be the conjugate base. So when you see this, look at the sodium part, right? Because the sodium is just there so you get the cyanide in solution. The spectator ions, that solubility rule, rule number 1. Okay? So by looking at these, you should be able to, I can calculate the moles of conjugate base. I can calculate the moles of the conjugate acid. And I just plug them in. All right, you see how? The moles of, I don't care, conjugate base. All right, how would you get it? Yeah, do the big M, exactly. Big M equals the moles over the liters. And we have 0.25 of it. Well, I'm not even there yet. I'm getting the moles first. I guess I could have done that, but then the liters is 50 mils, 0.05 liters. .0125. Now I do the same thing for the conjugate acid. Let's see. So that one's 0.2 moles. And my volume was, that one's 40 mils. That's 0.04 liters. So that should be, what, 0.008? Okay. So, substitute some stuff in here. I should end up with pH. Now the pKa we just said was negative log, and I told you what the Ka was. So let's write negative log. Well, 4.9 times 10 to negative 10. Just write everything out, not just skip anything. Plus the log. Now the conjugate base moles has to be on top. Conjugate moles acid on the bottom. So 0.0125 all over, yeah, there it is, 0.08, thank you. Okay. See what you get. Anybody get a number? 9.5. Okay, good. That's what I got. Well, 9.50 or something. Yeah. Okay, a bunch of us got 9.9 and a half. So make sure you can get that. I do. I start with the 0.0125 divided by 0.008. Right, hit equals, log, and then I do the 4.9% negative 10, log, hit the plus minus button, I'm done. Yeah, but you know what? If you're not so comfortable with the calculator, just do it in steps, it's fine. Okay. Everybody comfortable with 9.5? Alexa, did you get it? Okay, good deal. Okay. Now, there's usually a part B. And What is the pH if 100 mils of 0.01 molar HCl is added to the entire buffer solution? Okay. They're adding a strong acid. So is something going to change in my Henderson-Hasselbalch equation, right? Is something going to change in this? Will this change?
No.
Now will the pKa change? No, because I have to change the buffer to change the Ka, because the Ka goes with the buffer. I'm not changing the buffer. So we'll leave that the same. Okay, we should probably start writing some of this down. The pH, now we said that's that negative log of 4.9 times 10 to the negative 10. So that part didn't change. Okay. Now we have to have the moles of conjugate base or the moles of conjugate acid. We're adding an acid. We're adding a strong acid. We said what was going to react? The conjugate base. Okay, the conjugate base is going to react. And we said that amount is going to go down, right? Because if the conjugate base is reacting, it has to go down. So we're jumping ahead a little bit. We said our moles was 0.0125, right? That's what we said our moles of conjugate base was. And you just said it has to go down. So we put a minus sign. And we don't know what it is, but we'll figure it out. And the conjugate acid, that amount has to go up. So we should have a plus down there. So notice how the problem is exactly the same. You just got to change the moles of conjugate base a little bit. It amount is going to go down. It's reacting with the acid, strong acid. And then we're forming the conjugate acid of F minus. How do you figure out what this number is?
Does it depend on the moles of HCl?
Yeah. It's the moles of acid that you added. That's all it is. It's the moles of acid that you added. It's right here. That goes there. And remember, if they give you volume and concentration, you know moles. Okay. Yeah. Right? Yeah, because it's... Yeah. That amount. And go there. And there. Okay, so we should probably rewrite this whole mess. Ah. See. I screwed up my calculator here. Shoot.
Wouldn't it be the same pH for the top?
Yeah.
Oh, that's the 9.31 part that I didn't screw up. I screwed up in the other part. So what are you guys getting as an answer? Mine messed. I don't know. That's wrong. Oh, is this supposed to be what? I was trying to do it in steps, but it's not. My calculator's all messed up. What are you guys getting from numbers here? What you took the negative log of 4.9 to 10 negative 10? 9.30. Okay, and then what did you get for? Okay, so let's do this. 9.30, and then what did you get when you did that log of those two numbers?
I got 0.106.
0.106.
No.
What are you guys getting? 0.106. Something like this?
Yeah, that's it.
What? Oh, okay. Yeah, we should be more careful. So we ended up with. Okay. Okay. I don't know. These buttons are bad on there. Okay. So we could go on to the next question, but let's say you.
Why is it on the conjugate base you're subtracting conjugate?
Because we're adding an acid. The only thing that can react with it is the conjugate base. So that amount has to go down.
So when we add a base, it would be off.
Oh, good point. You hear what Jessica's saying? If I were to change the question to, get rid of that HCl and write, I'm adding NaOH, then this would be a plus, and this one guy would be a minus, right? Exactly. Okay, now, before we go on to the next question, pH originally was 9.5. Now it's 9.4. The solution got more acidic, slightly. It should have got more acidic because we added a strong acid. It didn't drop a whole lot, but it changed a little bit, right? 0.02, 0.08, or 0.09 units. Okay. Last one. Try this one. A buffer is prepared by adding 300 mils of 0.82 molar hypochlorous acid and 250 mils of 0.75 molar sodium hypochlorite. And I give you the Ka. What's the pH of the buffer? Now do part A. Don't jump to part B yet. There's a little twist there. Not sure, just ask. And we're not sure what to do here. Mm-hmm.
You log the conjugate and you get a negative, which is
Yeah, yeah. And number less than 1 will be a negative log. Okay. So that's how I set up my Henderson-Hasselbalch when I figured out the moles of conjugate base and the moles of conjugate acid. Okay. And then as a final answer, I got 7.34. Okay. Is everybody with me so far? Okay. Now these part B's are always, they look exactly the same, right? You end up with pH equals a negative, right? Negative log of 3.5. That pKa part doesn't change. And then you've got plus the log, right? And you know it's going to be something that's looking like this. And then you have to do minus and pluses and okay. Remember Jessica was even saying things change. The numerator, the 0.1875, is that a plus or a minus up there? Minus. The minus, right? Because we're adding an acid, the conjugate base has to react. This has to be minus. Bottom has to be a plus. Yeah, if we're adding a base, then the acid, conjugate acid has to react. So that would be a minus. Okay. And what's the number we're going to put in there? Find the moles of HCl. Yeah. You get 8.75 negative 3. Now, this isn't the whole story, though. I just want to make sure you're with me so far. Does everybody agree so far? Okay, now why isn't this the whole story? Does anyone catch it? Yeah, am I using buffer? No. Let's pretend we're using exactly 1/2 the buffer. Pretend. What would be times 0.5? What would be times 0.5?
Or is this
If we had a half, right? We could it's those initial amounts of conjugate acid and conjugate base. If it was a half, we'd put a half there, because we'd only have 1/2 the amount of the buffer. We only have 1/2 the amount of the conjugate base. We only have 1/2 the amount of conjugate acid to, right, initially. But I don't know what the fraction is. I'm just guessing a half. We should calculate what the exact fraction is. Whoa! Why are you using 25? What's the buffer? The 25 mils has nothing to do with the buffer. They took 100 mils of the buffer. What fraction of the buffer did they take? It would be what over what? Fraction of the buffer used would be what over what? Okay. Okay. Here's one. Here's one guess. 100 over 300. What's wrong with that? Yeah, you forgot about this guy. All right. So the bottom really should be. All right. That's the fraction. What is 100 divided by 550? It's like 0.18 all the time. 0.1818. 0.182 or something, right? So that's what has to go in here. Whoa! Yeah, you don't want. Cause you got to think of it conceptually. What's going on here? My moles of conjugate base is the red number, right? That's the number I want to modify. That's the number of moles of HCl.
I have a question. Where did it have 8.7?
All right. That's the number of moles. So that's going to be really just 0.02 times 0.35 moles per liter. That's another way to do it. I think that's faster than using the equations, but either way works. We have to figure out how much acid we added. So the moles of HCl is going to 3. That's why I got those numbers. So you have to take 0.182 times the 0.1875 minus 8.75 times 3. Okay, we've got 30 seconds to get an answer here. Who's the winner? It's not going to be me. I'm not even close. Final answer. 7.13 is one guess. Oh, we're not in consensus yet.
Yeah.
Okay. There's two 7.13s. I bet you that's it. 7.3. That's got to be it. 7.13.
That's the entire process.
So come by if you have some questions. I'd be glad to help you out with this stuff.